And here to talk to us about how capacitors work is JayBee. Take it away, JayBee.
Thank you, Brandon. Well, capacitors, another one of those mystery components in electronics that is hard for people to understand how they work because you can't visualize it very much. At first, let's talk a little bit about what is a capacitor. The schematic diagram of a capacitor, the symbol, is actually quite descriptive. It looks like two plates with a wire connected to each of them, and nothing in between. There's actually not nothing in between, of course, but there's no electrical connection. So you have two plates that are very, very close together, separated by some kind of insulation that's called a dielectric. One of those fancy electronic terms. It's just an insulation, but there's different dielectrics used in different types of capacitors. So the way it works, because these two plates are so close together, something happens electrically on this plate, it affects what happens on that plate without there being a direct connection. And that's the key. Say, for instance, I connected a battery. I'll put it through a switch. It's a crappy switch, but you get the idea. So when I close that switch, it comes down, current flows from the battery, this is the positive terminal of the battery, and piles up positive charges on this plate. Those positive charges repel any other positive charges that happen to be in the neighborhood, including the ones that are on this plate. So the current leaves that plate, and we get a balancing negative charge here. When it's all done, the charge across this capacitor, the voltage on that capacitor, is the same as the battery voltage out here. And that happened without an electrical connection in the middle, just the dielectric.
What is the dielectric usually made from?
The dielectrics are made of many different types of materials. There are ceramic dielectrics, there are tantalum dielectrics, there's polypropylene dielectrics, all kinds of plastics are used. Just about any kind of an insulator you can think of has been used in capacitors, some more successfully than others. But think of it as just a simple, very thin insulating material. For instance, I've got a bunch of capacitors here on my bench. Come in all kinds of different shapes, sizes. Here's a little tiny one. This one's in between size. And somewhere around the shop here I've got some big humongous ones, but I can't find them right now. They're hiding somewhere. Big giant capacitors. They all look different, but they all work the same way. They just have different characteristics because they're made out of different materials. Now, I described electrons flowing around. We can't see electrons flowing around, but we can see water flowing. And here we are with a water-powered capacitor that I put together here to demonstrate how it works. On this side, this is our battery. It's not charged yet. I haven't put any water in there. Let's do that. Let's charge that battery up. Let me get some water. Now our battery is all charged up, but the switches out here, you see I've got two paths. I got a big tube here, I got a small tube here. We'll talk about why the two different sizes in a little bit.
So wait a minute.
Yeah.
Does this mean that I can power my electric car on water?
No, but you can power your water-powered car on water. I think that's been done. Was that not done? I think they were called steam engines.
This is true. Back when you were a kid, they used to make those.
Yes, yes. I was a teenager back then.
Really?
And they were quite a lot of fun. I knew Mr. Stanley personally.
Did you?
The Stanley steamer.
Excellent.
So, after that rude interruption, let me continue. Got that, Brandon? Let me continue.
Continue you shall.
So, we have this path for the water to flow. If I step over to the other side, we have a water capacitor. This bucket represents this plate of the capacitor.
So that would be the positive bucket.
Well, it would be once I put a positive current into it.
Okay.
Right now it's kind of neutral. It's got a little bit in there, but not much. But you see there's no water connection between here and this side. This is the other plate of the capacitor, and that's got the red colored water in there. I made it different colors so you could see there's none of the blue water going to flow into the red side, but it is going to have an influence. Let's make it go, huh? This is exciting. All right, I'm going to throw the switch and watch what happens. Water is flowing. The bucket is filling up. And once it gets enough charge, the red water line moves down. So there's current flowing in here and there's current flowing out there, but there's no water connection between the two. Exactly how a capacitor works. Oh, this is fantastic, isn't it? Yes, it is. Now, you say, what happens if we want it to go the other way? Let's try it out. I need my bucket. Otherwise, we'll have a big mess. If I take my battery and I make it a negative charge now, look what happens. The current flows the other way. In this case, it's water current, and the red water flows up, back up into that plate of that capacitor. That's exactly what happens with a real capacitor in a situation where it's different positive and negative supplies. Perfect. All right. We'll turn that switch off now. Why do I have this small tube? Let's make some marks here. What we're going to do, I'll take these off because that's from another run. I'm going to put a mark on here where the red water is right now. And we're going to time how fast that goes down when I open the big tube. First I got to charge my capacitor, my battery, don't I? Here we go. Count it out. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010, 1011, 1012, 1013. There goes the red down because the float is going up now. 1016, 1017, 1018, 1019. About 20 seconds to get it to here. All right. Let's discharge the capacitor again. All right. There we go. Turn the switch off. Recharge the battery. Now before we do this, let's talk about the difference between these two tubes. This is a big tube, provides very small resistance to the flow of the water current. This is a smaller tube, higher resistance. We're going to flow the water through the higher resistance into our capacitor and time it out to see how long it takes for the red water to get from here to here. About 20 seconds the first time. Here we go. Is the water flowing? Yes, it is. But it's flowing slower, isn't it? Am I counting? No, I'm not counting. I should be counting. 1006, 1007, 1008, 1009, 1010, 1011, 1012, 1013, 1014, 1015, 1016, 1017, 18, 19, 20, 21, 22, 23, 24. The red water just started flowing. 25, 26, 27, 28, 29, 30, 31, 32. Come on, red water. Come on, red water. Come on, red water. We need the red water to be flowing. It is, but it's going very slowly. And that is the precise point of this part of the experiment. With bigger resistance to current flow, the slower the capacitor charges. It's charging, red water is going down, but it's going very slowly because we've got more resistance in the circuit. That's the point of the whole thing. And that's a very important characteristic. That's exactly how electrical capacitors work in circuits with resistors. The value of the resistor, the value of the capacitor, the supply source voltage determine how fast things happen, and that can be used in lots of really interesting and cool ways. Okay, let's shut this off. So what we did, first we did this charge thing with very little resistance in the circuit and saw how fast the capacitor charged up. And then we added some resistance in here, and that slowed it up. That's a very important characteristic, and we're going to demonstrate that in a real circuit in just a minute. But before we do, let's talk about the values of these capacitors. What is the value used for capacitance? It's the farad. That's a funny term. It's named after Mr. Michael Faraday, and he did some of the advanced preliminary work in electromagnetism, and in honor of him, they made the value of capacitors the farad. The value selected for capacitors was the farad in honor of Mr. Michael Faraday, who did some of the very basic early work in electromagnetic theory. What happens between these two plates is electromagnetism, static charges, that sort of thing. And he did a lot of the advanced work, so they named the value of a capacitor farad in his honor. And they defined a farad, F, as the ratio between Q and V. So Q is the charge on the plate of the capacitor in coulombs. It's another one of those funky words that named after another old dead guy.
How do you spell that?
Coulomb. Coulomb. C-O-U-L-O-M-B. Or something close to that.
Thank you.
Divided by the voltage. So if you have 1 coulomb and that develops a voltage of 1 volt, that capacitor value is 1 farad. Turns out a farad capacitor is humongous! Huge! Not a practical number at all. So, you get a capacitor like this, which is a very common one, and you read the value on it, and it says 47 mu F. What the heck is that? 47 mu F. Well, in electronics, a lot of scientific stuff. Mu means micro. Micro is 1 millionth. That's a micro. Microfarad. This is 47 microfarads, so it's 47 millionths of a farad. That goes to show you how big a farad is. It's a big thing. And then that's a common value range, but you also run into nanofarads. And F, nano is, add 3 more zeros, a billionth of a farad. Or one of my favorites, a picofarad. Add 3 more zeros, and it's a trillionth of a farad. PF, puff. That's called puff. It's not Puff the Magic Dragon, it's picofarad. Or back in the days when I knew Mr. Stanley of the steamer years, we called it the microfarad, or if you really wanted to be cool, it's the Mickey Mike. But today, it's a picofarad. Common values. This particular little capacitor here, if I can read it, it says 153K. 153K. 1530,000. So that's 0.15 microfarads, or 150,000 nanofarads, 150 nanofarads. That's how the values work. All right, let's see some real electronic circuits now, right? Oh, who's that? Someone at my door.
Oh, hello.
Hello, yes.
Faraday.
Michael Faraday, Professor, I'm so glad to meet you.
I was wondering if I could borrow a cup of sugar.
Cup of sugar, certainly, certainly. One moment, please. Here you go.
There's blue water.
Oh!
Are you making meth?
No, I'm not making meth.
Weird. Well, anyway, I heard you were talking about me. They were talking over at the VFW launch because...
Yes, I mentioned you earlier because you were honored in having the value used for electronic capacitors named after you.
What the hell are those?
Well, you'll have to watch the video on YouTube, and I go through the whole thing and explain what they are. But your work in electromagnetic and electrostatics was instrumental to the development of capacitors. Without capacitors, we couldn't have the electronics we have today. So we thank you very much for that.
And you've named them after me.
They named them after you, named the value after you, the farad.
Wow.
That's quite nice, huh?
That was an honor I did not expect.
Well, and apparently you died too soon and didn't realize it.
What are you talking about?
I understood that you've been dead for about 120 years or so.
Oh my god. You're right. I gotta get the hell out of here. Okay.
So here's the circuit. That's the equivalent of the water circuit. Our supply is going to go in here. That is connected to two paths, two different resistors, a low value here, a higher value here, with a switch for each one so we can switch them in and out. And then those two are connected to this capacitor. And this loop of wire is just so we can connect the oscilloscope so we can monitor what's going on this plate of that capacitor. We're going to use the oscilloscope to monitor that. And a little bit about the basics of an oscilloscope. This is the one that I use here all the time. It's a digital storage oscilloscope, which means it digitizes the input signals and saves them so you can manipulate them, you can analyze them, you can expand them, you can send them to your PC, you can do lots of different things with them. Be kind of cool to see if I could send one to YouTube. We'll try that someday. All an oscilloscope is a voltmeter, but it does it in a graphical fashion. On the vertical will be the voltage. On the horizontal is time. Time here, voltage there. I'm going to set the triggering on this oscilloscope. Triggering, what is that? The trigger is what starts the oscilloscope to scan, and it'll scan just one time and save that image, and we'll see it. I'm going to set it to trigger on channel 1. Channel 1, I have this voltage probe connected, and I'm going to put that on that loop of wire. Okay, and down at the bottom it gives you the scale. Channel 1 is 5 volts per division. Each one of these divisions represents 5 volts. We're working with a 10 volt power supply, so that'll work out nicely. And the horizontal scale is 2 milliseconds, 2,000ths of a second, 2 milliseconds per division. Alright, let's connect up the power supply. I have a DC power supply here right now. And I'm going to throw a switch on the low value resistor, and let's see what we get. And there it is. The oscilloscope triggered, and you can see the voltage on that capacitor went up, but it didn't go up instantaneously, it went up slowly. The speed that goes up depends upon the value of the resistor and the value of the capacitor, and how far it goes depends upon the supply voltage. Let's try the other channel now.
So before you start, we're on the 100 ohm resistor?
That's correct. We're on 100 ohms right now.
And we're sending it through what? The capacitor, what is the value?
That's a 2.2 microfarad capacitor.
Okay.
Yeah.
Great.
Okay. I'll clear the scope. I'll clear the scope. And we'll switch on the 1000 ohm resistor. And look at that waveform. It's coming out much slower. That characteristic of capacitors and resistor circuits is used in lots of different ways, as we mentioned before. The fact that the resistance, the value of the resistance, the value of the capacitor determines how fast the voltage rises on the capacitor. Very important characteristic. Now let's look at another thing. Using the oscilloscope, I'm going to connect on channel 2. This is a current probe. Instead of showing us voltage, as we have on channel 1, channel 2 is going to show us the current that flows through this current probe. The arrows on the current probe indicate the direction of current. I'll connect this up. It's tough to get my fingers in. There we go. Okay, so let's take a look at the same circuit now with an AC voltage source. Let's draw a little circuit diagram of what we're going to do. We have an AC voltage source, which is usually drawn like that. The little symbol indicates it's an AC source, and that's my trusty WaveTech function generator. It's going to go through a resistor to the capacitor, like so. Okay. Now, what's going to happen with an AC source, because this is going up and down, just like with the water supply, when I went up and down, the current's going to flow in and flow back out. And the way that the capacitor resists that current flow is a function of the frequency of the AC source. It's a very important characteristic of capacitors. So the voltage across this capacitor depends upon the frequency of the source, of course this resistor, which is going to drop some of the voltage, and the value of the capacitor will determine what its equivalent AC resistance is. Now we can monitor that here. I have set up 2 meters. This one shows the voltage from the AC source itself, that's right here, and this one shows the voltage across the capacitor out here. I've got the AC source set right now for you see we lost power again. Has a habit of doing that. I have the AC source set now for about 200 hertz. That's the frequency, and I'm going to set the voltage at approximately 5 volts. There, that's pretty close there. Switch is on for the 100 ohm resistor. The voltage across the capacitor is 2.98 volts. So the AC resistance of that capacitor is roughly equivalent to the 100 ohm resistor, because we're losing about half the voltage through the resistor and the other half is left for the capacitor. But if I increase the frequency of the AC source now by a factor of 10 up to 2000 hertz, 2 kilohertz, I'll readjust to get back up to 5 volts. There we are. And I'm down to 0.4 volts across the capacitor. So as we discussed up here, as the frequency goes up, the capacitive reactance or capacitance AC resistance goes down. It comes closer to a short circuit. We lose most of the voltage across the resistor, and just a little bit is left for the capacitor. That's how capacitors work in an AC circuit. Kill it. One of the most common applications or uses of capacitors is to decouple a power supply circuit. What the heck does that fancy word mean? It means to make it quiet when it would otherwise be noisy. Here I've put together this little circuit, a couple of integrated circuits. It doesn't really do anything except generate some pulses, but it will illustrate our purpose. If you look at the oscilloscope, the top trace are the pulses. Expand it out here, you can see that a little bit, that this circuit is putting out. And the bottom trace is the actual power supply terminal of that integrated circuit. And you can see every time this switches, we get a little noise on here, quite a bit of noise. This is 1 volt per division, so that's a whole volt worth of noise. You can imagine if you had a big printed circuit board with lots of ICs doing lots of switching and lots of things going on, the power supply gets very, very noisy, and that'll keep the circuit from functioning the way it's designed. If you're familiar with motherboards or any kind of boards, you see capacitors sprinkled all around that board, usually around the periphery, but also inside. Those are decoupling capacitors, and here's what they do. Those are connected to the power voltage rail and ground right near the integrated circuits. That's what I'll do right here. There, the noise is gone. Just with that capacitor. Very, very important characteristic of capacitors.
Take it out, back in.
Take it out. There's the noise on the supply rail. Put it back in. Noise is gone. Ta-da!
Go. Go.
Oh, you ready?